I'm Gil. I'm going to talk about making shatter attacks great again. But first, I want to say a very big thank you and a big kudos to all the organizing crew and the volunteers for making this happen, despite the crazy times we're in. So great job, guys. Okay, a bit about me. So I lead the R&D in Accenture Security Israel, formerly Maglan. And we do development of offensive and defensive tools. We do vulnerability research, do some general cybersecurity related innovation, and also AI security. So if this sounds interesting, ping me. We're always looking for bright minds to join us. Now, what are we going to talk about today? So we're going to give a bit of background history about shatter attacks, how they came to be, how they were mitigated in Windows Vista. Then we're going to talk about our reincarnation of them in the context of two main use cases. The first is breaking sandboxes. The second one is evading EDRs. We're going to talk a little bit about possible mitigations, and we're going to show a demo that will hopefully work. So let's start. So once upon a time, shatter attacks, they were introduced in 2002. They were used mainly as a way to do privilege escalation on Windows. So the way it would work, you would have some Win32 service running the system and making the big mistake of showing some user interface, some GUI to the user on the user's desktop. And then a user, even a guest user, could actually send a bunch of specially crafted Windows messages to this GUI, which would eventually cause code execution in the service and with system privileges. So the way it would work, we have the attacker over here, this nice snake, have the target process, which shows a piece of GUI that, among other things, includes an edit box. And we assume now that edit box buffer, like the buffer that stores the actual contents of the edit box, is in this constant address. So what an attacker would do, he will first send a set text message with the shell code he wants to run. So since this message copies a string to the edit box, this shellcode should be null-free, which is not a big problem. So he sent this message. The shellcode is now in the edit box, meaning at this address, 2000 hexa. Then the attacker would need to know this address. So this can be done, for example, by doing some recon in advance and doing some reversing or debugging and knowing that this is the static address that always holds the buffer of the edit box for the specific version of the service, for example. And then he would simply send a WM timer message. And one of the params this message receives is actually the address of the callbacks that needs to be executed. And basically, once he sends this message, the shellcode gets executed and we're all done. Pretty simple. So Microsoft, of course, patched this. Well, the first patch was actually to not handle WM timer messages for a non-previously registered timer, which seems kind of obvious and quite funny didn't do it like that in advance. So what this means is that actually an attacker now has to first call set timer API in the context of the target process, which is something he cannot do unless he already has some code injected into it, which kind of fits a perfect purpose, so that was good. And also Microsoft fixed all of their services not to show any GUI on the user desktop, and of course probably updated their best practices guidelines that everybody ignored, but that kind of put a stop to this simple vulnerability being used in the wild. Now, if we think a little bit in more general, what is actually the problem here that caused this privilege escalation vulnerability? So the first one was the lack of access control. So the fact that a process running as a low privileged user, even guest, could send Windows messages to a high privileged process, even a system process, that's one problem. The second one was the lack of namespace isolation in terms of Windows sessions and desktops. So there is no good reason for user processes and services to be running on the same Windows desktop. The third one is the fact that the Win32 service exposed the user interface directly instead of the way it's done today of running some client utility with a little Tracon or something like that, which runs with low privileges as opposed to the service running high privileges. And the fourth one, which is like more generic and is rooted deep in the design of the Win32 GUI subsystem, is actually the fact that you can send a Windows message across process boundaries that contains a pointer to a callback that is to be executed in the target process. Well, that's a big problem by itself. And so with Windows Vista, most of those issues were fixed. So Microsoft introduced the so-called UIPI, user interface privileges isolation, which basically added a new label to each process. It could be either low, medium, high, or system. So medium was the default one used for non-elevated processes. High was used for elevated ones. And low was used, for example, for the Internet Explorer renderer process that we wanted to run with even lower privileges than the normal processes. And then what this new mechanism would actually do is that you could no longer send Windows messages from low integrity level processes to high integrity level processes. Okay, that's that. So the second thing that was introduced in Vista is session zero isolation, which meant that all Windows services were now running in a distinct Windows session. So previously, the first user logon session was session zero, which was shared with all the Win32 services. That was the way in Windows XP, for example. But starting with Vista and onwards, services would run in session zero, whether the first user logon session was session one. And then if there were more users, that would get sessions 2, 3, etc. The third thing Microsoft did in that regard, to preserve backwards compatibility for services that for some reason still wanted to show a GUI directly, is that if a service tried to show a piece of GUI, the user would receive this funny looking message. And if he did the mistake of clicking view message, he would be redirected to a special desktop that contained the UI shown by the service. So that was very good. And actually it put a stop to shatter attacks altogether because they could no longer be used for escalating privileges. And of course they were quite forgotten until we came along. Not really, but let's skip that story. So the first use case we're going to talk about is actually commercial sandboxes. So we had a project where we needed to do some vulnerability research and assessment of a commercial sandbox to find weaknesses. So this sandbox, I've not disclosed its name because it was a client, but basically the concept was that we want to isolate between trusted and untrusted processes. So untrusted ones, which were running inside the sandbox, are processes that communicate with the internet directly, like we can think of, for example, web browsers, stuff like that. Whereas trusted processes are the ones that actually access and process sensitive corporate data, like documents, etc., and have access to the corporate network. And basically, this sandbox wanted to isolate between them so that if, for example, some client-side attack against code execution in the browser, it will not be able to do any further damage or collect any information. So this sandbox, it implemented like all the possible isolation in all relevant domains you can think of. So both file system and registry. So trusted and untrusted processes had a different view of the file system and registry. Did network isolation so that trusted processes can access the local network, the corporate network, whereas untrusted processes can access the internet. And it also implemented isolation for Win32 GUI, so you couldn't like copy-paste stuff between them, and you couldn't perform GDI operations like taking screenshots, and you couldn't send Windows messages between trusted and untrusted processes. So we were in quite a bit of a difficult situation there as an attacker. because actually the file system and registry were implemented using kernel mini filters. They were quite solid and quite difficult to exploit. And also, they implemented process isolation using object callbacks, the OB registered callbacks API, which actually didn't allow processes to open, like a process running in the untrusted environment couldn't open a process in the trusted environment for writing. So that was the first thing we tried. Like we wanted to, for example, try injecting code to a trusted process, but that was denied. So we couldn't open a process which was trusted with write access, but we actually were able to open it with read access, which proved useful afterwards, as we'll see. So then we were thinking, okay, so what else can we do? Or in other words, what is the weakest link here? And not surprisingly, there was one, which was the Win32 UI isolation. And the reason it was the weakest link is it was actually implemented by user mode hooks. Since, as we know, since PageGuard came along, kernel mode hooks for APIs are not really feasible. So the way it would work, for example, let's say I'm running in an untrusted process, want to send a Windows message to a trusted one. So basically, the moment I call send message, there's an inline hook intercepting it, and basically denying the call, returning me access denied. But since this is a user mode hook in the process we are executing, we were actually able to remove them using quite a generic method of comparing the entry points of all exported symbols from all loaded modules, and then comparing them in memory versus the copy on disk, taking relocations into account, of course. And whenever we saw a difference, we would simply overwrite the memory version with the one from the disk, which effectively removed all the hooks. So now we were actually able to send messages across isolation boundaries. So, and then wondered how that might be useful. So since it was before this lecture, I banged my head on the wall for a day or two until Shatter attacks came along. And then basically, if you remember, we talked about Windows Vista mitigating Shatter attacks used for previous escalation. But the thing that Microsoft actually didn't address is the fact that you still had Windows messages that could be sent across process boundaries, at least processes running the same integrity level, that contained callbacks, which means addresses, pointers that are interpreted in the context of the target process and executed. So this looked like something that can eventually be exploited. And actually, if you remember, we talked in the beginning about a basic Shatter attack based on the WM timer message, but apparently there are a bunch of other Windows messages that had the same pattern of having an argument, which is a callback. So I was stupid enough to go over and enumerate them myself instead of looking for other folks who've already done it. But this is what I found. So there are a number of them in rich edit controls used for customizing different behaviors, such as autocorrect and stuff like that. The list view control has a bunch of them for sorting elements, and basically allowing the user to provide a custom compare callback for the sorting. And also the tree view had the same. So there's a message you can send to a tree view that sorts the elements of the tree, and it actually, you can give it a callback to the custom compare function, which proved very useful, as we'll soon see. So here's a sample for using this tree view message to execute code. So this snippet by itself is not really useful to us because, well, it requires write access to the target process in order to allocate memory and write to it. But this will prove useful to understand what we did further. Okay, so I'm going to go over it quite quickly. So basically what this code does, it injects code specifically into the registry editor. So it first finds the tree view that's inside it. It gets the process ID, opens the process for all access, and then allocates memory, which is executable, and writes the payload, which is the shellcode we want to run, into the target process, into registry editor. Then it obtains the root item from the tree view, and then initializes the TV sorts CB struct, which basically contains the parent, which is the root item, which represents the subtree that we want to sort. It has the address of the compare function, which is in our case the address of our shellcode, and an L param, which is null, which we don't care about. Then it allocates memory in order to copy this TV sort CB struct into the target process. And finally, it sends this tvm sort children CB message to the target process. And when it's sent, it starts sorting the tree view. And the moment it first needs to compare two elements in order to implement the sorting, it calls the callback. But the callback points to our shellcode, which gets executed, and we're very happy. So that's the way it works. Now, as I said before, it's not really helpful for us as it is, because we still need to find a way to copy some shellcode into the target process. Moreover, we need to put the shellcode into executable memory, because otherwise DEP will prevent it from running. Now, step back a little bit. If you're looking into code injection in a bit more general fashion, like I said, we need to first copy the shellcode into some address we know of in the target process, and we need to make sure it's an executable region of memory. So either we copy it to executable memory up front, or we need to migrate it into it using some method. And eventually we need to trigger execution. So at this stage, we have the trigger, which is the tree view sorting message. We still need to find a way to copy our shellcode into executable memory in the process, which is what we're going to show now. Okay, so this is a high-level overview of what we did. So first, we used an edit box in the target process and sent to it a WM set text message in order to copy our shellcode into the process. Now, we used the Unicode flavor of send message, and that way we're actually able to inject shellcode that does contain nulls, but not double nulls, because that's the null terminator for Unicode. Next, we need to find the address of the shellcode. So in the original Shatter attacks, it was they assumed that the address is static, and they simply hard-coded it. But we wanted to do it dynamically. And at this stage, we actually leverage the fact that we have read access to the target process. And so we simply scanned, we opened the target process for reading, scanned its memory using virtual query X to get our memory region at a time, until we found the pattern, until the pattern matched the shellcode we copied into edit box. So now we had the address of our shellcode in the target process memory. Next, we needed to migrate the shellcode to some executable memory. So what we did, we used the same memory scanning technique to find the region of memory, which is read, write, execute. We assumed it does exist in the target process. We'll talk about it in a moment. And once we found it, we used a status bar to actually migrate the shellcode. So what's very nice about the status bar, as opposed to the edit box, is that actually it has a set text and get text messages. And the argument they receive is not serialized, but instead treated as a pointer to data in the target process. So we could use set text to copy the shellcode from the edit box buffer into the status bar. And then we could use get text to actually copy the shellcode from the status bar to our target executable address. So now we had our shellcode in executable memory, and we could use the tree view in order to execute it. So that's the way it would work on a high level. Now, how did we actually use it? So luckily for us, Windows Explorer on Win 7 has all of these controls that we need. And what's more important, Windows Explorer, in the context of this sandbox, was actually treated as a trusted process. So that means that if you are able to inject code into Explorer, we win. So the Windows Explorer, so it has an edit box right here that serves as the search bar. So it's not strictly an edit box, like it has a different Windows class, but it does support WM set text with the same semantics, which is what's important for us. An edit box. So it has also a tree view right here. And it also has a status bar. So its status bar is actually hidden. You cannot see it, but it's there and it's useful nevertheless. And also what was very important and even crucial was that this Explorer in Win 7 also contains a read-write executable region of memory without doing anything special. So just a vanilla Windows 7 will have RWX memory in Windows Explorer. And now let's go over the attack sequence in a bit more detail. So we have a shellcode without double nulls. We find the following UI elements in our target process, which is Explorer exe. We find an edit box, a tree view, and a status bar. Then we also find an RWX executable memory region inside Explorer by simply iterating over all the memory regions and checking their protection flags. So now we have this target address that we define as being in the slack space, like in the end of the memory region, which is all nulls. Next, we allocate a TV sort CB struct and initialize it. We allocate a payload buffer which contains both our shellcode and the struct. And we copy this shellcode into the edit box using WM set text, the Unicode flavor. Next, we scan the target process to find this payload in this address. Then we define the address of the TV source CB struct as being this initial address plus the length of the shellcode, which brings us here. Next, we migrate the shellcode to executable memory. So as we said earlier, we're using the status bar for this. So we're sending a set text W message to copy the buffer from this initial payload address, which is null terminated, into the status bar. Then we use get text W to copy it to target other, which is now in executable memory. And then finally, we have everything in place, and we send the tvm salt children CB message with the address of our struct over here, and it works. We have code execution. Now, there are two small pitfalls that we need to overcome to actually weaponize it and be able to use it robustly. The first one is that actually the compare function, which compares pairs of elements in the tree view while sorting, can be called multiple times, which is probably not something we really want. We don't really want our shellcode to run multiple times. So to overcome this on 64 bits, we simply add this bit of assembly which we append it to the shellcode, which basically overrides the beginning of itself with the ret instruction. It returns immediately. The second pitfall, so what that means actually that after the first time it runs, the next time the compare function is invoked, it doesn't do anything, it doesn't run our shellcode, instead it simply returns, which is what we want. Now the second pitfall is that actually in order to have all the controls, all the Windows controls we need a file explorer window to be open, which is not always the case. Like there are folks like me using Total Commander, so they will not have file explorer windows open at any time. So to overcome this, we actually found out that you can use shell execute and pass it an SW hide flag so that we can open File Explorer without the user seeing anything. And then we open it, inject the shellcode, run it, and close the window afterwards. So this is it, and then it worked. It worked, we were able to break the sandbox, we're very happy. Now onto the second use case. Second thing we thought we could do with this technique is to actually perform code injection into Explorer that EDRs will not detect because they're probably not familiar with this technique and it doesn't do anything suspicious, so we thought it might fly. And as we all know, the challenge with EDRs, if we're talking about code injection, is that they're actually very sensitive to processes, opening other processes and writing to their memory, etc. So we wanted to implement code injection without this. And of course, Shatter attacks came to our help once more. There was, however, an extra challenge since we wanted to do this on Windows 10 this time. And the issue now was that there's actually no read-write execute memory in Windows Explorer on Windows 10, which is what you would expect, and now it is the case. But we still had a few ideas. So if you remember, we used the tvm salt children CB, which receives a callback to a compare function. And then we decided to look into it in a bit more detail. So this is the struct. It has the parent, which is the subtree we want to sort. It has the compare function, which is our callback. And this is the signature of the compare func. So it receives 3 arguments. The last one is actually the same lparam from the tvsort CB struct, so we can control it easily. The other 2 are the lparam fields of the tree view items being compared. So we could actually control them as well because we are able to inject data into the process. So we can inject a TV item struct into the target process. And then we can send the set TV item message. So since we can control the lparams of the tree view, we can actually control these 2 arguments. So it might be a bit difficult to control their order because it's difficult to say what will be the order of the comparisons that the sorting algorithm does. But as we'll see in the next slide, it doesn't really matter. So the bottom line is we can call some function, and any function we want, and pass it 3 arguments we control, or almost control. And then we started looking for a function that we can call that might help us gain some executable memory to use. So the first one we thought of was, of course, virtual alloc. So virtual alloc looks good. The first 3 arguments we can control. The problem is that the last one, which is the most important one, because it contains the protection flags, is actually out of our reach. That's the first argument. So we were sad. The runner-up was virtual protect. So this looked a lot more promising because actually the first 3 arguments are the important ones. The first 2 identify the memory region, its offset and size, address and size. The third one contains a protection flag. This is good. And the last one, like it's simply an out param to receive the old protection flags. So we thought, okay, we'll pass a null there, or hope that a null will be passed by itself. And then it would work. But unfortunately, Microsoft didn't really want anyone to do that, as the documentation clearly says that if you pass a null or an invalid address, the function will fail. So we were sad once more. Now, there are a bunch of other virtual alloc or virtual protect-like functions, a lot more than I expected. And they all have even more arguments, so even worse than the first 2. But then one of my team members, Ran, he had a bright idea. He said, okay, there's a function called heap create that creates a new heap. And actually, its first argument has some optional flags, options. And one of them is heap create enable execute, which basically allows the user to create an executable heap. So I guess it might be useful like for just-in-time compilers, stuff like that. And of course, it was very useful to us. And since heap create receives 3 arguments, we were very happy this time. So what we did, so we actually set all the lparam fields of all the elements in the tree view with the value of heap create enable execute. So as you remember, Never mind. As you remember, the compare function, the first two arguments are the L params of the three items being compared. So we said that we cannot really control the order, but we can simply pass this same value in both of them and it would work. And then basically we're able to call heap create using the tvm salt children cb trick. And we were able to create an executable heap, which means we now had read, write, execute memory, and we're back to the same scenario as on Windows 7. However, there was another small challenge. So it turned out that actually the status bar, it does some filtering. Basically what it does, it filters the white character counterparts of the non-printable small ASCII characters, which means that for each white character of the form B, which is some byte, and 00, if B is between 1 and 1F, except for 9, which is a tab character, then basically it transforms it into 2000, which is a space character. It does some synthesization. So when we only wanted to, as in the context of the sandbox, when we only wanted to copy a shellcode, it was fine because you can craft a shellcode without special characters of your choosing. But in this case, it was a problem. And another problem was that we also had some double nulls or even 4 consecutive nulls that were that we needed to pass around as part of the structs for setting the L params in the tree view, etc. So what we did in order to overcome this is to actually come up with a very careful procedure for copying data into the process through the edit box and status bar. So more concretely, in order to overcome multiple consecutive nulls, we actually found, when we looked for an executable memory region, we made sure that we find a region which contains, which is all zeros, which was very easy because we used heap create to contain it, so the heap was zeroed at first. And then if we needed to copy a bunch of nulls, we'd simply skip to the offset after the nulls, because you don't really need to copy them, they're already there. Now, in order to overcome the filtering by the status bar, we did the following. So let's assume this is the source buffer we want to copy. So AABB can be copied nicely, but 0500 will be sanitized to 2000, which is bad. And then CC is also fine, and etc. So we would first copy AABB to offset 0 in the target, which works. But then instead of copying 0500, which would be filtered, we actually copy BB05 again to offset 1, and it would look like this. So we overwrite the BB character again, but it doesn't really, there's no problem with that. So we now have 05, and then we jump to copying 00CC to offset 3. So eventually we have the entire source buffer copied. So basically, in order to copy a filtered white character of the form B00, we first copy B with the previous one, and then we copy 00 with the next one. And basically, that was it. Now it worked. So we were able to set up all the memory in the target process in order to invoke heap create with the correct parameters. And then once we called it, we had RWX memory. And then it was back to the Win7 scenario that we already talked about. And we were able to inject code into Explorer. Now, just to give you a glimpse of how it looked like when the EDR was looking at us doing this. So this is the leading EDR. So just to create a baseline for this test, we did a good old create remote thread to load library just to see that the alert is triggered. So it shouted, alert severity, inject code unknown app, etc. And those are the low-level events. And this is the high-level alert. The application injected code into system process, as we would expect from any self-respecting EDR. Then when we used our injector, which is Shatter X over here, So there are no alerts, so we don't show it. Now there are a few events here, but the reason for this mainly is because we implemented the proof of concept in Python and used py2exe to package it. So the first, all but the last event here actually caused by py2exe doing stuff. And the last one is actually an open process. So if you remember, we did use open process to open the target process explorer for reading. So this CDR did complain about this, but it didn't sound an alert, so we consider it a success. Yeah, success. Okay, so we're almost done. So let's do a quick recap. So we took a very old security-related design issue in Windows that wasn't really fixed. So the fixes in Vista did contain it, but the root cause for the Shatter attack wasn't really addressed. So in the root cause is the fact that pointers being passed in Windows messages are a giant mess. So you have pointers for some messages that are actually treated as strings and they're serialized and copied to the target process. You have pointers to strings that are simply treated as pointer to data in the remote process, which helped us migrate the shellcode from one place to another. And sometimes, which is the most dangerous thing, you have pointers, you have arguments to Windows messages, which are actually passed around and are treated as pointers to callbacks in the target process that are simply executed. And you can give any address you want and it will get executed. So the combination of them gave us all the primitives we needed to implement code injection. So we could allocate read, write, execute memory using heap create. We can write to an arbitrary address. We can copy code around from place to place, and we could execute a specific pointer we wanted, which is more than you actually need. And now, in terms of possible mitigations for this, so the most trivial one would be to say, okay, let's hook send message and block the dangerous Windows messages or sanitize the callbacks or something like that. The problem is that user mode hooks, like we said, are not really could not be really treated as a security mechanism because they can be disabled. But luckily for us, Windows actually does provide a very robust method for filtering Windows messages, which is the set Windows hookiex API with the appropriate WH hook types. We didn't implement it, but it should work. So I think that would be like the best mitigation for this. And now let's see a demo. I hope it works. Okay, so you have here a VM. We're going to run Shatter run from Explorer, which should run something from Explorer. Now the sample shellcode you'll see now, basically all it does is pop up a message box. Just so that you can show and demonstrate that this message box is actually opened from Windows Explorer. So let's run it, hope for the best. Okay, so it says that, of course, didn't work. Let's try this again. Okay, now it worked. It says that no read-write execute memory was found, so it created it.
אבי, אתה פה? להפעיל לי את המדונה?
Now, as you see, it is actually blocked.
יש פה סאונדמן להפעיל לי את המדונה?
Well, the message box is here, the Explorer icon over there. And also, if we take spy++,
תודה.
find
ענבל,
it,
שמתי את זה פה, ענבל לא יודעת.
and go to the process,
פה זה לא
we'll open
מצטלם,
it
נכון?
eventually. Spy is a bit slow on this.
אתם תיתנו לי 10 שניות? תודה. אתם לא יודעים, סבבה.
All right, so we see this is open from Explorer. So what happens now is actually, since our code called send message with the sorting message, it actually waits for the shellcode to quit because the Explorer is currently trying to sort it and is stuck in the callback. So click OK, it finishes. We're all good. Obviously, we can put any shellcode we want there. The shellcode would probably, if you want to use it for real, would probably open a new thread and then execute in it so it doesn't block anything. but you get the idea. Okay, back here, we're actually done. So thank you very much. This is my email. You can scan this QR code. It also contains my email. So if you have any questions, suggestions, remarks, I'll be very glad to hear them. Send me a line. Thank you very much.